pause. This is an error like this. So class is about to start, so
I see that.
I can talk more after class.
All right, that'd be great. Thanks a lot.
So hi, so let's get started. So hopefully you all turned in your so your assignments. If you didn't quite finish it, or you want to revise something, you can turn it in by roughly this time. So tomorrow you only get so 10% off. If you turn in one before and afterwards, and you'd like one specifically graded and not the other, please email us or leave a comment so it's clear. So which one to grade? So let's see. So now there's the locality-sensitive hashing homework, which has been posted for about a week already. It's due so a week from today. So there were some small changes in the assignment after it was posted. Let's see what happens if I open this. So I didn't. So I thought I posted the new one on the internet, but I just so I suppose I didn't. So I'll change that after class. But these numbers, I updated these numbers last minute, and I meant to make this also 0.92 and this also 0.45, so that's going to be symmetric. So I'll change that. Hopefully that's a small. That's a pretty small change. And then so the other parts are about so generating some high-dimensional vectors, like we talked about in class, and then doing some stuff with so with the angular the hashing for the angular LSH. And then you don't actually have to implement all so the stuff with the we implement the thing with bands and see this actually works. You actually need to get to pretty large sizes to actually see this working effectively. But if you want to go ahead and do it, you can do it as part of the bonus. Okay. So then today we're finishing up kind of this section on distances and so similarities. There are a couple things I didn't quite finish last lecture, so I'll start with that, and then we'll see some alternatives to locality-sensitive hashing. Also, I want to kind of stop, and we'll kind of discuss some of maybe some of the ethical implications and the fairness implications of the modeling choices you make in choosing these transformations and these distances. Then starting next week, we'll start the next section on clustering. And we'll spend the next week and a half on that. Okay. And then, so let's see. So great. So so the first thing I want to start with is a few other distances I think are important just to be aware of. There's this so distance called so called the edit distance, and so this is defined between so strings. So we've dealt with text before, large pieces of text, and if you treat the text as character, doing charactergrams, you're effectively treating the text as just these long strings. This works when the documents are extremely large. The edit distance is useful when these strings are going to be short. And so it's basically, it counts the number of the number of operations, so which is delete, add, so replace, to turn one string so into another. All right. So if I look at the edit distance between two strings, let's say mines and it matters how I spell it. So in smiles, then I can do these operations where I can add an S here, smines, smize, and so smiles. So this is 1, 1, 2, 3. So it's 3 steps here. I could have, after I had smiles, I could have done a replace where I replaced the N with an L, and then it would have only been 2 steps. So sometimes you're allowed to do replace, sometimes you can just add and delete, and the distance is slightly different. But you and maybe I could say the cost of doing a replace is like 1.5 times the cost of doing either an add or delete. This is basically how it works. So the kind of important thing to know about this is that this works really only if the distance is so it's very small, right? So if I'm doing this between words and the edit distance between them is like 6, I can basically get from like any 2 words, right? Especially if I can do like a replace. So you can move very far in the space with a small number of steps. Where this is really, really useful, though, is checking for if something is spelled correctly, right? So your spell checker is doing this. If you see a word and it's not in the dictionary, what does it do? It tries to find all words which have a similar spelling, and so it makes suggestions for you that this word is off by not too much. Okay, you can do specialized things where you can say, well, if I'm changing one vowel into another vowel, that might be less than changing into a consonant, because that's more likely of a misspelling mistake. Or if 2 letters are next to each other on the keyboard, you might be more likely to mistype one instead of the other, right? So you might be able to kind of change the cost here. The other place that this is used very frequently is like inside search engines. So you'll see it'll give you suggestions. Maybe you actually meant to search for this, and it's because it's using some version of edit distance inside. But there's there's no real way to do locality-sensitive hashing for the edit distance, which is actually effective. Okay, so a lot of these techniques for very large, kind of scalable nearest neighbor search are kind of, there are certain ways that they're known not to work for this distance. So this has kind of been a major, something people have wanted to do for a long time, and there are certain results that say it's probably not possible. Now there might be something other than LSH you can use, which is effective, and they have engineered solutions which are effective in practice. What they do for search engines is that they just store a lot of possible misspellings, right? And so they just kind of have these pre-computed because they have so much space, right? But if you want to kind of automate something like this, this is much harder. Okay. And then yeah, question. So things like for individual words, like if you're typing and there's spaces between words, your text editor knows to spell check each word and give suggestions. And for strings you might search between, it'll do an edit distance between individual words, but it might also do that between short strings you might type into a search engine. Something probably as long as a tweet is probably too long. It's going to be it's computationally too hard. You have to search over all the possible transformations to do this, basically. And so this is pretty hard to do. Yeah.
Is it also always return the lowest number of possible edits?
Yeah, right. So it's going to try and find the shortest path between this. So think of, this would be like a classic question in algorithms to solve with like dynamic programming, right? So if you have it between here, you can expand all possible ways of changing the letters and trying to get to here. And if you use an A* search, you're probably going to be somewhat efficient, right? But it's essentially, to compute it, you want to find the shortest possible path. Okay. So great. So then the other thing we've been talking about is if I have so if I have my data, say A and B, are going to be these vectors in so d dimensions. Then we had mentioned a number of these distances. This LP family of distances. We mentioned that if you set, if you map A bar down to down so that it's a unit vector, right? So it's a unit vector. Then we could use the cosine distance or the angular distance, and these are kind of very popular ones. There are other ones you can use in these cases, but these are the popular ones. I want to now talk about one more kind of way you can map this down, where you do, I normalize it in a way which is different, where I basically do an L1 normalization instead. Okay, and I also want to ensure that each coordinate is greater or equal than 0. Okay, so technically, I actually want it to be strictly greater than 0. I'll explain that in a second. So I'm going to define some space. So this is going to be it's like a triangle in a. So this is going to include all vectors in our D such that the norm of x, the L1 norm of x, is exactly 1, and each xi is greater or equal than 0. And then I'll also define some, I'll put a 0 down here, and this will mean something slightly different, where still it's L1 normalized, and each xi now has to be strictly greater than 0. Okay, so this is interesting because then I can think of the coordinates. So after I have something in the space, I can think of x1, x2, x3, up to xd. I can think of these as values between, every value has to be between 0 and 1. Right, so I can think of them in this way, and they have to, and this, because it's L1 normalized, it means that the sum equals I up to D of xi is exactly equal to 1. Okay, so they're all greater than 0 or all greater or equal than 0, and they sum up to 1. So what could something like this represent? It's another way to think about a vector like this. I heard some muttering that sounded close to correct. Yes. So I can think of this as a probability distribution, right? So now it's describing a probability over these coordinates, right? So if this value is 0.2, if this is 0.2, then I can say the probability x is equal to 3 is equal to 0.2. Right? It's effectively saying this, right? So, or the third object I'm kind of wondering about here. So, one natural way to get something like this is if I'm doing like this this bag of words modeling on like a text document. I basically start by doing a count of every word. I have this really long vector, and for every word that occurs, there's a coordinate that corresponds with that word, and I count how many times this word appears. Okay, so this is good because the count has to be greater or equal than 0, and so then I can normalize this, L1 normalize it, and it becomes the probability. If I pick a random word on this page, the probability it will be that the word corresponded to each of the coordinates. Okay, so now it's a very natural way to represent this bag of words this representation. This sort of thing comes up in other places as well. Every year, a bunch of people try to do projects that have to do with, I'm calculating these different statistics over different states in the U.S., and I want to compare states. There's a problem where some states like California are much larger than other states, almost like Wyoming in terms of population, and this kind of makes things hard to compare. One way that helps a little bit is to try and normalize these one particular value across the states, and then I can think of having a 50-dimensional vector that I can compare. Right, so maybe I have different distribution, different characteristics. Each one is a 50-dimensional vector for the 50 different states, right? And then I can compare these in this probability space. Okay, so this normalization is useful, and it gives rise to certain types of distances are natural between between probability distributions. The most kind of probably common and so the most common and like famous one is going to be the Kale divergence, and so this one is defined. So I'll say P is in D minus 1, P and also Q. Right, so I have two probability distributions, and I'm saying that none of the characteristics can possibly be 0 probability. In that case, then the Kale divergence between P and Q, and this is often actually written in this strange notation where you do P. So this, so it's P, and then you have these double bars, and then Q, and I'll explain kind of why that is. And then this is defined as I equals 1 to D, PI natural log of PI over QI. Okay. So So one of the first things you can see is that this distance is not going to be symmetric. Okay, so if I do D, the KL divergence between P and Q, that's different than between Q and P. And so this double bar notation, part of the reason for that is to remind you that I can't just swap the order of P and Q, the distance will actually change. All right, so one of the next things to see is that when I have this natural log in there and I'm dealing with probabilities, that this says something about, it looks kind of like something from information theory, or like has to do with entropy. And so those, if you have that intuition, you might not if you haven't like taken a signal processing class or something like that, but if you have the intuition, then this intuition is right. This is saying something like, if I know the if I know the distribution Q, how many extra bits do I need in order to express the distribution P? Okay, so if you know distribution Q, how many extra bits do I need to convey the distribution P? So if I know I'm on the opposite side of a channel and I need to send bits across, I know the other party knows the value of the Q distribution, and I want to update it and say, no, it's actually this P distribution, here's the difference, then it basically corresponds so to this. So it's really telling you kind of something very natural about the underlying probability distributions. The fact that it's not symmetric and it also violates the triangle inequality means that this is not a metric. There's a variant of this called the so it's called the Jensen Shannon distance, which is an attempt to make this symmetric. So I'm not going to write it up. The details aren't important. But so there are other variants in this space that have to do with modeling the probability distribution, and in that sense, they're like slightly more natural. Okay, so if you think it's probability distribution, you should consider one of these distances instead. There are other ones which are actually metrics. Notice there are some strange things that, for instance, I need here, which implies that no pi is exactly equal to 0. So if I'm using this on my bag of words representation and I didn't see a word, I can't quite apply this. So you need to kind of, it turns out a reasonable thing to do is to add a count of one word to everything, and this kind of lifts everything up, and this kind of smooths out the distance in some way, which is a reasonable thing to do. If you look in the textbook I'm writing, I have an example where so I have an example where I actually work through this. The other thing to mention is that there's a nice geometric intuition of what this this space delta, let's say delta 2 looks like, or in general delta D. What I can do is I can expand up to distance 1 along each of these axes. Right, so this is 1, 0, 0. This is 0, 1, 0, and this is 0, 0, 1. And I can do this in higher dimensions as well. And then the space corresponds with a triangle here, some filled-in triangle. And so that's why I use triangle to represent it. So this is known as like the D-1 simplex. Okay, and then if I exclude the 0, it means that it's an open simplex. It doesn't have boundary. I can't have any of the coordinates be 0. Okay, so that would mean it would just the filled-in part, but not the part on the boundary. So there's, and this intuition extends to higher dimensions. Okay. All right, so that was wrapping up from last lecture. Okay, so I want to start by revisiting talking about these word vector so embeddings. Okay, and so this is I mentioned this briefly in one of the previous lectures, but this takes a large corpus of text. Think the so something huge like the entire web or like all of Wikipedia, right? And what's it, the text looks like the story, said, right? As this text that goes on, it's across all the documents. And so what I want to do is to take each word here, and it will occur multiple times in the corpus, and I'm somehow going to map this word into this space. So V story, it's going to be an element of a roughly 300-dimensional space. So there are some newer things that have come out in the last couple of years. They're using like 1,024 dimensions, but some very, very high dimensional space. So and the kind of the basis for how these words they're mapped into the space is not quite, but something like they're trying to preserve. They're trying to embed them in a space where the idea is to use either use the Euclidean so distance to tell whether two vectors are similar, or use the cosine similarity. So these are kind of the two natural kind of distances or similarities that are often used in this space. So if you normalize first, then you might want to use the cosine similarity. It turns out, though, that the length of the vector carries some information as well, so you might want to use the Euclidean distance instead. These are commonly what's used. However, the construction of them will start with this, usually this something like this, this word count vector, where I'm counting every time the word story appears, I look at its neighborhood and I see what other words are nearby in this neighborhood. And I keep track of the counts of all those in some vector. I define some information theoretic distance in between these. So it starts with from text to these vectors, which are the number of dimension here is going to be like so something like 1 million, however many words up here, and it's going to keep a word count in the neighborhood of each word. So the story is next to the and said. Usually the neighborhood side would be like 3 instead. So I look at words within a distance of 3 in these neighborhoods. Okay, and I'm going to get these really high dimensional vectors that are going to be completely sparse. They're mainly zeros. Okay, and then I'm going to define some distance. It's going to be an information. So it's going to be an information theoretic distance that has to do with the so what's called PPMI, which is the pointwise. So it's a positive pointwise mutual information. Okay, so this is derived in a way similar to the Kähler divergence, but it's not exactly the same. It can handle zeros in terms of these things, and then it maps to our, say, 300. So it maps to a 300-dimensional space, and these are going to be these word vectors, these word vector embeddings. Okay, so this is basically the pipeline, how it works. The word vector embeddings, even though these vectors, these really, really high-dimensional vectors, are trying to measure the PPMI distance between them, or the similarity when they embed them, they're supposed to correspond with Euclidean or the cosine similarity. Okay, later in the semester, we'll talk about ways of doing this dimensionality reduction that can preserve either Euclidean distance or some other sort of distance. Is also fine to use in some cases. It turns out to do this, they actually instead learn this with a neural net, with a deep net instead. I'm not going to go through the details of exactly how they do it. It turns out in some cases doing like principal component analysis, which we'll talk about later in class, works nearly as well. So the difference is there's some small differences, but it's not a huge difference. Yeah. So it's the positive so point-wise mutual information. It's so you can write something. It's written something like max of 0, probability of 2 words I and J jointly occurring, divided by the probability word I occurs versus the word J occurs. So you can take. So there's some rationale behind this. This is kind of the base of what's doing. I'm not going to totally go through the details of why this is used. There are variants of it that use something else instead. This is not the only way to do it, but this is the most common way to do it. And kind of a lot of this is kind of washed away in terms of some. They try and optimize their neural net to maximize on some prediction tasks of neighborhoods of words, and so kind of this is a useful thing to know, but it's not actually essential to know how to do it. Okay, they're creating these large neighborhood word count vectors. They're really high dimensional. They think some information distance between them is the right thing to use, whether it's PPMI or it could be the KL divergence, although that's not going to be symmetric, and there's other issues, but you could plug something else in there, and then you eventually want to map it to a low dimensional space. So, okay, and then once you're in the low dimensional space, typical thing is either the cosine similarity or the Euclidean distance. These are what's used. So that's why in the previous parts I focus on those distances because they're often those work well within algorithms we'll see in the rest of the semester. Okay, so I wanted to give this as an example for one reason. An example, you get high dimensional vectors that make sense. I don't have this issue with height and weight of all these coordinates. That's usually the first thing you think of. These are all going to be kind of, the coordinates are all kind of, they don't have different units into them. Okay. So the other reason I wanted to talk about these is that there's some neat properties that occur with these vectors. You can do things like you can embed a vector for the word king. You can embed a vector for the word man, and you can embed and you can embed a vector for the word woman. All right, and so if you take these vectors, now they're vectors in some space. I can do operations on them. So if I do let me actually move these around. So if I do something where I do king plus so v woman so minus v man, I can think of this as the king. I have the man, the woman, and I can think of them as points. Now they're in the 300-dimensional space, so I'll draw them in 2 dimensions. This essentially tells me a vector, right from man to woman. That's what I do when v woman minus v man. And if I add this to king, this is a vector from the origin. If I add it to king, it's going to be over here. And so then it's likely that the closest word over here, if I look in some neighborhood around this vector, which is the result of this operation, this is often the vector for queen. Okay, so there's this notion of coded of like the gender in between words from be man to be woman, and I can say transfer that, apply it onto king, and I'll often find queen, right? So this sort of information is encoded. There's other stuff that's often in there, so the word for doctor and V and DR, the abbreviation for doctor, are often going to be very close to each other. So if I look at the cosine distance or the Euclidean distance between vectors, these are often going to be very close because they're two words which can be used somewhat interchangeably. All right, so there's this nice power about these, and this really captured the attention of a lot of the research community. These are often used inside of pipeline for other predictive tasks that have to do with that have to do with text. I don't know how to process text. Instead, I map every text word to one of these vectors, and then I try and build a classifier or clustering afterwards. So the one issue with these vectors is that there is this gender encoded in here, and actually this doctor vector is usually not over here, but it's usually over here. So we're closer to the man side than the woman side. Actually, if I took this, so this might be over here, and then there might be another vector. So the so the vector for nurse might be over here. So if I took this same vector from man to woman and I applied it on doctor, I might end up with so it's pointing towards nurse. And this occurs because these are built on either all of Wikipedia or all of the internet, and that data tends to encode this sort of so this sort of relationship. Okay, but then this is used in downstream tasks, right? And it's blindly used and said that this is now a way to represent these concepts. And so I kind of want to maybe discuss for a bit, like kind of have a discussion, what can go wrong about this? What can we possibly do as data scientists and modelers and analysts? What can you possibly do if is this okay or is not okay? If it's not okay, what's the right way to deal with something like this? Is it okay to use these embeddings if they improve classification performance on, say, how well someone will do in a job? But they may also encode bias that they're not going to recommend a woman for a job as a doctor. They'll recommend her for a job as a nurse, even if she has the same qualifications as a man applying for the job.
I was just going to say, like, would that depend on the distribution from wherever we're grabbing this information up? And
sure.
Maybe one thing to do would be to try to not get such a biased distribution of them if you're going to use them.
Yeah, so it'd be great if there was like text we could learn of that we knew was going to be unbiased, right? So, but these are built on basically the teams who have built this. There's like a team from Stanford and like a team from Google that have been building the most widely used of these, and they basically try and get all of the text they can find, right? So grabbing from the entire web, basically there are these public crawls of the web that they're using to build these. And so, and the more data they get, the more accuracy they end up getting in these downstream tasks.
wouldn't that still be subject to the fact that information on the internet is intrinsically sexist? Or
Sure, yeah. So it's kind of been accepted that probably the sort of concepts which are encoded in here are encoded because those are inherent in the data. Yeah, so they get the data from the internet because, I mean, that's where they can access the data from. Or if you, yeah.
So I know a male nurse who told me he was one of 2 male nurses in his entire class. So what's reflected here is something that's happening in reality that's being measured by this data. Now you can say that we don't want that to be the case, but how are you going to do that in the system?
Yeah, so I mean, it is reflected in the data on which this is built. So the kind of like I'm not saying there's a right or a wrong answer, but you know, if I'm using these then in some downstream task, maybe this tells me yes, there happen to be more female nurses than there are some male nurses. Maybe that's something I realized from this data. Maybe there are other subtle things that I didn't, you know, that you can confirm or other properties that are in this data. So in some senses, capturing something that maybe is useful to know. Right.
Well, so if we know the bias exists and we have these vectors, we could try to just shorten that distance between like the doctor and the nurse from the man and the woman. We could just try to remove that through scaling.
Yeah. So we can try and take this out of the data after we've created these representations. Yeah.
Seems like bias is only a function of the purpose you're using the data for. The data is the data. It's the reality of the data set you've chosen, which may have inherent bias or it may be entirely accurate. So bias seems like a function of intent.
So there are ways where bias is a function of intent. There are some technical definitions, some legal definitions of what is allowed and so not allowed. There's this concept called disparate impact. Okay, and so this is encoded into law, and it says that if there's something used in I think it's like it's known as like the 3/5 rule. So if there's something you use, a hiring process, it's usually using the concept of hiring, but it could be in other like loans and other ways as well, that has more than a 3/5, 3 to 5 ratio error in certain protected classes of people, whether it's man or women or different ethnic backgrounds, then you have violated, even if you did not intend to, but if the results say, if I look at the fraction of each protected class, say males versus females, who applied for the job or applied for the loan, and what fraction were given the loan, and that's off by more than a 3/5 ratio measured in some way, then this violates some disparate impact. You may not have intended to do it, and maybe you used a system that used these word vector embeddings in order to do that, and that somehow encoded that for doctors. I happen to hire a higher fraction of the males who applied than the females applied, or with nurses the same way, right? Not saying doctor is strictly better than nurse, but so there's like if I hired too many male nurses out of the fraction who applied, then I've violated this law, right? So there are laws on the books in here that have nothing to do with the intent.
I was just going to add
Sure.
to the data part. It's like with medical data specifically, one of the things that happens often is that we have a body of data that pertains to a very specific demographic, and we use that as if it was the scientific definition for all demographics. So in that way, I think bias is not a function of your data. You're just sort of grabbing what you have there, which is incomplete. And I maybe propose a solution for that would be you need some domain expert to give you guidance to these in which you're going to, how you're going to weight the data so that you try to get rid of those.
Yeah, so so that brings up another point, which is a separate issue than this particular issue, that if your data is imbalanced, right? So I mentioned, I think on Monday, if you train some percentages based on, population of the weights of kids in the United States, a large percentage of these are sort of ancestry from Europe, and so the weights are, usually around that sort of that sort of child. But if a child is from has a different ethnicity, those may not actually reflect what's going on. There's some ways to try and downweight some population, upweight another population to try and account for this imbalance, and this can have other sorts of effects as well. Any other comments on this? I'll say a few other things. So one thing you can do is that there's this direction, which is in encoding gender. So it's this gender direction. I can kind of, and it turns out I can learn this fairly well inside of these embeddings. I can find these pairs, man, woman, boy, girl, he, she, that are encoded fairly accurately. Turns out using names of common male and female names works fairly well. Also, and there's pretty much one vector which encodes this with some noise. So one thing you can do is you can actually try and remove this direction from the data. Remember, I'm in 300-dimensional space, and I can map it down to a, say, 299-dimensional space, right? In the two-dimensional picture I've shown, it looks like I would lose a lot here. But if I have this the gender direction, I can basically project or orthogonal to it. And hopefully what it does is it maps the man and the woman vector close to each other, the queen and the king direction pretty close to each other. And as a side effect, maybe it doesn't make the doctor and nurse direction directly close to each other, but it removes the distinction along some direction associated with so that's associated with the gender. Okay, so man and woman won't exactly map to each other. Man is used in a lot of other connotations, like if I say "oh man," or other ways it's used in speech. So they're not going to be exactly encoding this direction, but so they won't be exactly on top of each other. You'll still capture some other stuff in the other 299 directions. But as you mentioned, once I've done this, I've lost some information that there happen to be more female nurses and more more male doctors. This information in the data is lost, right? So is that a good trade-off? So maybe, right? So but maybe you've lost something that is important for prediction, right? If the prediction of how well someone will do in the job is worse, then maybe you don't want to do that. But then there are laws. Maybe there's some. If you know this is going on, maybe you feel moral imperative to try and do something about it. But maybe you say the bottom line matters. I need to get the prediction accuracy as high as possible, and you say, this will give me the most the most useful predictor. So I'm not here to tell you which is the right way and which is the wrong way. I just want to kind of so I want to try and raise these issues. Okay. So one thing I'll say is like this occurs and it's explicitly been measured, and this kind of projection technique is shown to kind of, you can reduce this sort of bias in the data or this sort of associations in the data. You know, there are other cases where you're going to be making modeling choices. I'm going to create a model with 3 grams instead of 4 grams over my data. And when I do this, it's going to, when I built these, I changed the window size from a radius of 3 to a radius of 4. This changes the representation so in certain ways. It may not be I can explicitly measure, say, a gender association, which has there's some protected classes which you can see that it's going to affect. But you might notice by looking at how your classifier or your clustering or something works afterwards that it's making some changes, right? You know, as a data scientist, do you have an obligation to kind of try and understand if there is a bias in those changes, even if it's not having explicitly to do with the data you've collected, it has to do with just these modeling choices you've made, which is there inherent bias in 3 to 4 radius? I don't know.
Does that sort of depend on what necessarily you're trying to do with your sort of data analysis? Like in this case, you could try and make the comparison of like, what if I try and map out all the text on the internet and figure out what sort of biases exist? In that case, like you definitely want to know sort of the distance between them and them. But if you're trying to do something where you're trying to explicitly disallow sort of that bias, then you would need to sort of do this like logical projection to try and account for that.
Yeah, so I think what you're saying is that it's going to depend on what you're using this for, right? If you're using it to learn something about the data, not trying, and then maybe you don't want to try and take this out, you're not worried about these modeling differences. If you're using it for some task which is protected under some law, then maybe by law you have to, but maybe there's some gray area in between.
Like maybe if you were doing like medical records analysis, like certainly there would be a dynamic difference between like how men and women react to some type of drug. In which case, you know, even like races might respond differently, or ages might respond differently to a certain type of drug. In that case, it would be very important to have sort of these biases based on like protected classes.
Yeah, that's a great point. Yep. So I mean, maybe finding this correlation is actually important, right? This is, and there's not a harm coming from this, but you're actually you can use this to kind of make like it's actually telling you how to treat people better in terms of medicine.
I'm curious about what sort of effect this gentrification has if we remove it. For example, you know, would we lose, you know, an association with women with pregnancy and stuff like that? Like the distance between a man and pregnancy and woman in pregnancy would be equal.
Yeah, so that would probably be the case. So there's probably pregnancy would be up on it. I haven't. That's not one I've looked at, but it's probably up towards in that direction, and that would be, you know, that association would be squashed, right? The goal of this is to remove all of the gender information from these sort of things. Like in German and other languages, a lot more words have a gender association with them, and I don't think that necessarily. I mean, I guess actually I don't know. I don't know if that association shows up here as well, and that may be useful for kind of automatically know which der or den to put in front of the word when constructing language. Yeah. So great. So I mean, I think this was a good discussion. I'll try and have little breaks in other lectures later on where we bring up some of these issues. Okay, so there are a couple of other things I wanted to mention. So I just want to mention kind of a couple of other ways that you so that you generate data in RD. So what was a very common way to do this up until about 5 years ago, it was like the dominant way to do computer vision analysis of images until deep learning kind of took over this. Although if you see what deep learning is doing, it's inherently doing something kind of similar to what's going on here again. But there are these, the dominant way to understand these images, if you think of an image, is that it's a series of these pixels. And so I tried to come across super well, but you can, each pixel is essentially one color. It's a color square inside the image. And you can treat each of these pixels as a single element in one long vector. Okay? So if an image is going to be 200 times 300, then I can represent this as a vector in our 200 times 300. So some really long would that be? 60,000 dimensional vector, and I can, and actually each color would usually has an RG and B value, red, green, blue. That's 3 values, so I get 3 times as many. So maybe times 3, so it's a 1.8 million dimension, or no, 180,000 dimensional vector, and I can compare images in this way. Okay, so this was like the first approach, and it doesn't work that well. It kind of tells you if an image is more blue or more, it might be about water, right? Because it has a lot of blue in here. If it has green in it, then it might be has some forest in there. It would tell you that sort of stuff. Okay, so this was maybe greater than not 200. So it's like greater than 20 years ago. This was kind of the common way to try and deal with images, and it did not work very well. Okay, there were search engines built this way for images. This used to be a big kind of thing. How can we search for images the same way we can search the web? Well, and this way did not work very well. So what happened about 20 years ago were these SIF vectors, which maps data, which maps pieces of images into a 256 dimensional space, and the right distance to use based on empirical tests was using the Euclidean distance in between these vectors. Okay, so this didn't use the entire vector, but what it did is it would pick some point and it would take some neighborhood around here. And so I have, like, think of this pixel, it has these neighborhoods. I'm actually not going to go into all the detail. And it would map this point, this individual point, into a 256 dimensional space based on the neighborhood information in some way. SIFT stood for Scale Invariant Feature Transform. It kind of captured, if I took the same picture, the same point was in multiple images, but one had a lot more pixels than the other because it was either high resolution or it was zoomed out, then, or zoomed in, then it should still capture the same information. It measured it at multiple scales. It tried to deal with rotational symmetry in various ways. And each of the coordinates kind of has to do with, you can think of like, as like a gray value associated with it. And so we would try and do this for all over the image, but it would only kind of keep them for more interesting points, points that were kind of extreme in the space. And that would have to do with these corners. So there might be another corner of the boat down here, and this would have a non-trivial SIF vector. And so there might be one here, and it would throw all these vectors into this big space, and then to search for similar images, you throw a bunch of these images and you see, say, what fraction of them hit, and you do something like the LSH trick with the min-hash vectors, where if there's a lot of them which are sufficiently close, you say what fraction of the images of the vectors hit. I probably have some common elements in between these. So sailboats will tend to have features associated with the sails. Cars have features associated with the wheels. Faces have features associated with parts of the eyes and the mouth and the ears. And you can learn those to kind of classify something fairly well. And this was the state of the art until about greater than so 5 years ago. And then came like the deep learning revolution. And if you look at what the lowest level of the best deep nets are doing, they essentially are learning something which is similar to these representations. The first couple levels of the deep net are kind of learning representations which effectively act like SIF features, and they're doing something somewhat similar in the basic transforms. It's not exactly the same. Since this 20 years ago, there have been other variants of this which maybe work slightly better, and essentially what ImageNet and these other deep nets are doing is some essentially variant on this at the beginning, but it's learning the parameters of it instead. Okay, so this is another place where these high-dimensional Euclidean vectors come from. Okay, so that's, didn't want to say anything too much more about that. All right. Okay, so what's needed in all of these, again, is this, so to quickly find, so the nearest, so to quickly find the nearest neighbors, okay? So I'm going to think of having some large data set P, which is going to be in RD. The size of P, we'll say, I want this to be, size of P is N, and this is large. And then given a, and so given a query Q in RD, I want to say quickly find, what I'm going to say is phi of P of Q, which is going to be the arg min data point in my set that minimizes the distance between P and Q, right? And I'll use the Euclidean distance. So I'm going to quickly find the nearest neighbor. Sometimes you want to find the k nearest neighbors, and instead, once you have the k nearest neighbors and you know some label or features with this, this is called, you can predict the labels on the query point Q. This is called a k nearest neighbor classifier. You can do versions of regression the same way. So this is kind of an important operation. It comes up in the SIF vectors, in the word vector embeddings, right? This is kind of an important thing to do, and Euclidean distance is the distance most studied here. Okay, and so I mentioned that locality-sensitive hashing can indeed solve this problem. You can basically set some threshold, and if you return to few points or no points, you can increase the threshold and kind of do a binary search on the threshold with LSH. Okay, so with LSH, with so binary search on tap until you have 1 point or k points in there, or you have not too many points and you check the distance with all the points which have been returned. Okay, so this works okay. LSH is not always the best thing to use here. So this, in super high dimensions, this is often pretty good, and it's general to a lot of types of distances, but it's not the only thing to use. And I mentioned that in D equals to 1, which is again a common case, I can use a binary tree, and this takes, I can do this in so an O of log n time. I can basically search down the binary tree, moving left or right each side, and then look at the two nearest neighbors. right? So in one dimension, I can do this very quickly as well. And this is way better than doing locality-sensitive hashing. Okay, so is there something in between? If D is 2 dimensions or 3 or 10 dimensions, is it better? Is there something else I can do other than doing locality-sensitive hashing? Does anyone know the answer to this question? Have you seen this in data structure class or someplace before? So KD trees, yes. So so I'm going to get to those. It turns out, I mean, in the worst case, those can be bad, but I'll kind of get to those in a couple slides. So it turns out in D equals 2, what I can use is what's called the so I can construct what's called the Born diagram, and I can again search this in O of log n time. And what this is saying is I've got my points P1, P2, P3, P4, and I can basically divide up the space. This is 2 dimensions, this is the plane, and I can draw these regions, and I can say that inside of each cell here, P1 is the closest, P2 is the closest here, P3 and P4 is the closest anywhere in here, right? So if my query point now falls over here, then I know that if I know I'm in this particular cell of the plane, I know P2 must be the closest. So kind of like binary search in one dimension, I'm basically just chopping up the one-dimensional interval, and I can figure out which cell I'm in log n time. It turns out I can construct the Born diagram in basically almost linear time, and that you can build something like a binary tree on top of it. Its complexity is basically linear in the plane. The problem is that in general, this size of the Born diagram is O of n to the d over 2 floor. So that means in 3 dimensions, it's n squared size. And 4 dimensions, n squared. In 5 dimensions, n cubed time, n cubed size. So that's just the size I need to represent all of kind of the vertices and edges and faces I get in this diagram. And so in order to answer a nearest neighbor query, it's equivalent to saying which cell am I in this diagram, and that becomes very complex as I get into high dimensions. So there's no way it's not even feasible to construct and store it. If n is a million squared or cubed is too large. So I can't even construct something that encodes the information other than just measuring the distance to all the points, right? So this kind of approach kind of breaks down after 2 dimensions. So what people typically let me add something else. So what typically is done for d greater or equal to 3 is they do what's called approximate nearest neighbor. Okay, and so what I want to do is to find a p in P such that the distance between P and Q is going to be greater, or it's going to be less than equal 1 plus epsilon. So I'll inflate this, think of epsilon like 0.1 times the distance between P star and Q, where P star is equal to R is the phi function, right? So this is P star is the true nearest neighbor. And say if epsilon is 0.1, then I'm inflating, I'm within 10% of the closest cost. Okay, so typically they'll relax upon to do an approximate nearest neighbor. And so really with locality-sensitive hashing, I'm only getting this sort of guarantee anyways. because if I'm doing better than this, I'm essentially encoding something like the Voronoi diagram, which is not possible. Okay, so so once I do approximate nearest neighbor, then I can start to do some more interesting things. And kind of the basic thing that works in D equals between 3 up to like 12 dimensions or so is some variant of the KD tree. Okay, so there are other things as well. They're like if you read a computational geometry book, you'll learn about quad trees and R trees and range trees, which may have better theoretical guarantees, but people in practice often use variants of this KD tree. Okay, and so what's going on here? Think of this point set on the left, and so you're kind of dividing and you're taking turns in every dimension. This is an illustration just in 2D, but I'm splitting like a binary search tree would in the x direction first. So I start with the x direction, and I split here. That's this split. I know if I want to look for a query point, I'm going to decide what is the x coordinate greater or less than this thing. And then I'm going to do the these next two splits in the y direction. And then the third time down, I'll switch to the z direction if I have it. Otherwise, I start cycling through these dimensions again, right? And then so this split, these splits here are in these dimensions and so forth, right? So now, if I'm given a query, let's say Q is here, okay, so then I can look at Q and I know I go to this whole, I'm going to look down this subtree, and then I'm going to look at the line splitting, this blue line splitting in the y direction, and I know I'm going to be above that, so I'm going to go down this way again, and then I'm going to go in this pink line splitting in the, right, so I'm going to go on this side here, on this side, and then on the right side of this pink line, and then I'll put me down here, and then I will compare, you know, the distance between Q and P10, right? This data point, which is over here. Okay, so now if I look at this and I draw a circle around Q, okay, and if there are no other points inside the circle, P10 I can tell that P10 is the nearest neighbor, okay, by looking at this distance here. All right, so if I've done this in the KD tree, I haven't quite satisfied that I know that P10 is actually the nearest neighbor, because this circle actually crosses over this boundary, this blue boundary, right? It doesn't cross over the pink boundary, so I know P9 is not closer. But it might cross over this blue boundary, so really I have to check down this tree again. So then I have to check down this tree, and I have to kind of search, well, did it also cross over this pink line? Well, no, it's all the way over here, so I can go down in towards this direction. All right, that was actually, yeah, so actually down to P8, and then I can also compare with P8, and maybe it looks like P8 is closer. Right, so P8 happened to be closer, and so I've done this. I have to do this backtracking in order to check. And so that's why I don't quite get a guarantee that it's only so logarithmic time, but in practice it works pretty well. Okay, and what happens actually, what's really important is that if I do this approximate nearest neighbor, maybe P10 is a sufficiently good approximate nearest neighbor, which means that I don't have to guarantee that the black circle doesn't cross any cell boundaries, but I can shrink it some small amount. I can shrink the black circle some small amount here into this green circle, and then maybe that green circle doesn't cross any of these boundaries. So then I can stop. Now I don't need to do this, this backtracking. Okay? And so maybe P8 was actually the right answer, but the distance to the query is pretty close to what it was to P10, so I'm satisfied with P10. And so I can stop earlier. So when I do this approximate version, where I relax my constraint of what if I can stop backtracking, this becomes much, much more efficient. Okay, and so this is kind of algorithms based on this. A generic KD tree will generally work from so dimensions 2 up through about, say, 12, or I've heard reports up to 20, depending. If the data is kind of nicely structured, it's not like full dimensional, then you can get up in even higher dimensions. Just using something like this. Works reasonably well. Definitely better than all pairs, and often better than LSH. So in higher dimensions, greater than 20, there's actually another trick you can do, which I'm not going to describe in full, but you want to make this so it's a data adaptive, so KD tree. And the idea is that I'm not going to cycle through the coordinate axes to do my splitting. I'm going to, if my data happens to lie in high dimensions, kind of like this, then I want to make sure I split this way. I split kind of orthogonal onto the data. So simple ways of doing this is either I can use, I can try a bunch of random directions and pick whichever one seems to split them the best. I can basically do a clustering of the data into 2 clusters, which we'll see starting next week, and then split at the midpoint of 2 representative points of the 2 clusters. I can do principal component analysis on the data, which we'll see in several weeks, and that'll give me some direction here, and then I can again take some orthogonal direction to orthogonal half space to that. And these allow me to usually get up to maybe D equals, say, 200, or sometimes even higher. So I've heard that on the so on the SIF vectors, some version of this was typically what was used as the nearest neighbor search. Some data adaptive KD tree with approximate nearest neighbors. Again, with the approximation, I make some modeling choice of what the distance is and how I create those features. So you shouldn't trust the distance all that much. So I have a couple more minutes. I just want to tell you one of the reasons why KD trees are hard to work in high dimensions, and why a bunch of stuff breaks down, even these approximate variants, is because there's this essentially battle between these squares, so squares versus circles. Okay, so the nearest neighbor in Euclidean space, I'm trying to basically search with a circular ball. I want to find the nearest neighbor defined by a circular ball. But I usually am decomposing my space based on these squares. And so data adaptivity helps a little bit. Turns out using L-infinity distance, which kind of gives a ball that looks like a square, doesn't necessarily help so all that much. That actually is harder in certain ways. But I just want to show you very quickly what happens, the difference between these squares and circles in high dimensions. So I want to think of a ball so a ball of radius 1, okay, and I want to say its volume, and this is equal to pi, if you don't know this offhand, so pi to d over 2 times the gamma function of d over 2 plus 1, and this is times the radius to the power d, but this is approximately equal to pi of d over 2 times d plus 2, so factorial, right? And So basically what happens as D, so this is factorial, right? So this is D, this is 1 times 2 times 3 up to times D over 2. So it's bigger than pi to the D over 2 once D starts getting larger. So that means this goes to 0 as D goes to infinity. Okay, so this volume essentially, if normalized this way, the volume essentially goes to 0, which is kind of unintuitive. Okay, so this is the ball of radius 1. Let's look at the smallest box which contains this ball. So that's going to be a box of radius 1. That means the side length going all the way across is going to be 2. So I'm going to say a box of side length 2. And the volume of this, the volume is going to be simply 2 to the D, right? That's how volume works. So as D gets larger, this is going to grow exponentially larger, right? This one is going to 0. Slowly, it eventually starts going to 0, where this, from the get-go, starts growing exponentially larger. So as I'm searching in a ball here, I'd like to find everything in a ball, but there's all this stuff in the box because it's so much bigger, and that's all I can constrain to. Okay, so there's the difference between these balls and boxes makes this high-dimensional search kind of very hard to deal with. So okay, so that was so I'll stop here for today, and then we'll have start clustering next week on Monday.